China just launched 88 rockets in a single year. That's more than double what they achieved 24 months ago, and the pace keeps accelerating. While SpaceX dominates with reusable boosters and rapid turnarounds, China quietly developed something different, a manufacturing system that treats rockets like products rolling off a car assembly line instead of handcrafted machines. How did they solve a problem that's stumped Western aerospace engineers for decades? And what happens when this production machine reaches full speed? The answer starts on December 20th at Wenchang Space Launch Site. A Long March 5 rocket pierced the night sky, carrying a payload to geostationary transfer orbit. This was the 10th Long March 5 flight, the 17th in the family series, and China's 88th launch of 2024 alone. Brigadier General Brian Sidari, Deputy Chief of Space Operations for Intelligence with the U.S. Space Force, didn't mince words at last month's Air and Space Forces Association conference. It is concerning how fast they've done it. But here's what makes this different from every other space race headline you've read. China isn't just launching more rockets. They've fundamentally changed how rockets get built in the first place. Traditional aerospace manufacturing works like this. Engineers forecast launches years in advance, build components based on those predictions, then store everything until assembly. The problem? Launch schedules change, designs get updated, satellites get delayed. By the time final assembly happens, you're often working with parts that were optimized for yesterday's requirements. This push system creates massive warehouses full of expensive components that may never fly, while simultaneously causing delays when the wrong parts were stockpiled. China's solution comes from an unexpected source, the automotive industry. They call it final assembly pull, and it flips the entire production model backwards. Nothing gets manufactured until final assembly actually needs it. When engineers start building a rocket booster, that triggers engine production. Engine production triggers parts fabrication. Parts fabrication triggers raw material orders. Every component moves through the supply chain because something downstream needs it right now, not because someone guessed it might be needed 6 months ago. Think about a restaurant during dinner rush. The old aerospace method is like cooking 100 meals at 5 p.m. based on what you think people might order, then hoping you guessed right. The pull system only starts cooking when someone actually places an order. Less waste, faster service, and you can adapt to what customers actually want instead of what you predicted they'd want. For rockets, this changes everything. When the launch manifest shifts, and it always shifts, the production system adapts in real time instead of scrambling to retrofit stored components. When a design improves mid-production, new units immediately incorporate the upgrade rather than waiting for old inventory to clear. The entire supply chain becomes responsive rather than predictive. But implementing this at aerospace scale required something else entirely. China built a coordinated national network connecting state-owned enterprises, research institutes, and private suppliers through digital platforms that provide real-time visibility across every link in the chain. Smart factories using AI and robotics can reconfigure assembly lines for different vehicle types instead of relying on fixed production setups that can only build one thing. According to China Aerospace Science and Technology Corporation, this represents a disruptive transformation of space hardware production. The numbers back it up. After orbiting roughly 200 satellites in 2023, China doubled that figure the following year while increasing launch tempo by over 30%. They're not just building more, they're building faster at lower cost with greater flexibility. And they're doing it because they have to. The global launch market is projected to explode by 2045, driven by massive satellite constellations for communications, Earth observation, and space-based internet. China plans 3 mega-constellations, Guowang, Qianfan, and Honghu 3, that will collectively require tens of thousands of satellites. The old handcrafted approach couldn't possibly scale to meet that demand. This is where the strategy gets really interesting. For decades, China's space program ran almost exclusively through state-owned enterprises, reliable but slow. Then, in 2014, the government opened Earth observation and commercial launches to private investment. The floodgates didn't open immediately, but they opened steadily. Policies clarified confusing regulations. Government contracts became accessible to private firms. Commercial space got officially designated as a strategic industry. By 2024, hundreds of Chinese space startups had emerged, backed by venture capital and serving both civilian and military customers. They're working on reusable rockets, satellite buses, on-orbit services, advanced engines, and space-grade processors. Companies like CAS Space and Landspace are rolling out rockets with reusable first stages this year. Newer players like Cosmoleap and Yushi Space are developing chopstick-style catching systems similar to SpaceX's approach. The government isn't just permitting this activity, they're actively accelerating it. The 2026 to 2035 space plan, currently in development, could streamline launch licensing and open major test facilities that were previously restricted to state programs. China's first dedicated commercial spaceport on Hainan Island started operations specifically to give private companies faster orbital access without queuing behind government missions. Here's the bottleneck, though, and it's significant. Even with 88 launches in 2024, that pace can't support plans for tens of thousands of satellites. SpaceX alone launched more than double China's entire national output. Most Chinese launches still use Long March rockets, serving government and science missions. Their launch pads have limited capacity, and commercial customers wait their turn. But watch what happens when those private rocket companies hit their stride. When reusable boosters start flying regularly. When the commercial spaceport reaches full capacity. When the pull-based manufacturing system enables rapid scaling. The infrastructure being built right now isn't designed for today's launch rate. It's designed for something much larger. This raises an obvious question. Why isn't the West doing the same thing? Why aren't more American or European companies replicating what works? SpaceX moves incredibly fast, but dozens of Chinese firms are simultaneously testing different reusable architectures, some like Falcon 9, some like Starship, some hybrid approaches. Over the past decade, American companies including Firefly, Sierra Nevada, Stoke, Relativity, Blue Origin, and Virgin Orbit have all pursued innovative designs. None have achieved SpaceX-level success or market dominance. The difference might be this. In China, being reusable and domestically produced is enough to attract government backing and strategic investment. In the US, any new launch company immediately competes against SpaceX, the company that invented the reusable orbital rocket market and currently dominates it. Investors see a company proposing, "We'll build our own Falcon 9," and ask why they should invest hundreds of millions to fight SpaceX head-on in a market SpaceX already owns. Some argue there's still room. Even with reuse and rapid cadence, Falcon 9 can't serve every customer. Custom schedules, specialized orbits, unique payload requirements, these create opportunities for alternatives. And when Starship reaches operational status, it still won't cover every mission profile. The market has space for multiple successful companies. But here's the strategic calculation China made that changes everything. They're not trying to build one company that can beat SpaceX. They're building an entire industrial ecosystem where competition drives innovation, while government coordination prevents duplication and ensures resources flow efficiently. Dozens of companies pursuing slightly different approaches, all benefiting from shared infrastructure, coordinated supply chains, and strategic direction. The pull manufacturing system enables this. When multiple rocket companies can draw from the same responsive supply chain, when smart factories can reconfigure for different designs, when the bottleneck shifts from manufacturing capacity to launch infrastructure, suddenly you're not betting on one company to succeed. You're creating conditions where the entire sector advances together. What happens when this system reaches full operational tempo? When those satellite constellations start deploying at scale? When launch costs continue dropping and access to orbit becomes routine rather than exceptional? The answers to those questions are being written right now in factories across China where the next generation of space hardware is taking shape, not one rocket at a time, but as a continuous production stream. So here's what we're really watching unfold. This isn't just about China launching more rockets or building bigger constellations. It's about fundamentally reimagining how space hardware gets produced at industrial scale. The West spent decades perfecting rockets as precision instruments, each one a masterpiece of engineering. China looked at that approach and asked a different question. What if we treated rockets like products instead of prototypes? The pull manufacturing system, the coordinated national network, the explosion of private space companies. These aren't separate initiatives. They're pieces of a larger strategy designed to turn space access from an exceptional capability into a routine industrial process. And the timeline matters. By the time Western companies recognize this shift and attempt to replicate it, China's ecosystem will have years of operational experience, refined processes, and economies of scale. Does this mean China wins the new space race? That's the wrong question. The real question is, what happens when two completely different approaches, SpaceX's vertically integrated innovation versus China's horizontally coordinated ecosystem, both succeed at scale? When launch costs crater and orbital access becomes abundant, the competition shifts from who can reach space to what gets built there. We're covering every development in this industrial transformation as it happens. If you want to understand where space manufacturing is headed, not just where it's been, hit that subscribe button for New Space Review. Drop a comment with your analysis. Are we watching the future of aerospace manufacturing take shape? Or is there a critical weakness in China's approach we haven't seen yet? Share this with anyone tracking the space industry, because this story is just getting started.